Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about India's Power Corporation having basically a marriage with E2S Power or thermal energy storage. So let's dive deep into it. So before we understand why the heck these two couples are making love to each other, we have to understand what exactly is the problem. Well, problem is renewable energy is intermittent. So far, we are only used to intermittent in our demand. So the idea is you can turn on whatever you want, whenever you want it. You have grid inertia, and based on that inertia slowdown, again, if you turn on a 10 megawatt load, let's say a metal furnace, boom, 10 megawatt load. How the heck power plants can compensate for it? It does not. There is inertia, there is physical spinning mass that slowly starts to slow down, because the heavier it is, the more time it's going to take to slow down. So computer is there. Okay, the RPM is 1500 RPM. Then it will notice, okay, the RPM is now 1499. Okay, RPM is now 1498. So it will start to detect. It's very slow process. Again, slow from a computer's point of view. From our side, it will look like it's happening 100 times a second. So computer will detect it and it's like, okay. Then it will trigger a warning where it's like, okay, I think there is a big load in the demand. Now it's an armed situation. Now it's like, okay, is the frequency still dropping? As in RPM? Yes. Then it's like, okay, open up steam valve. More power, more pressure. Now you can compensate for that 10 megawatt. That's how our grid somehow successfully manages supply and demand, because demand has no throttle. It can go up and down whenever it wants, but supply has a throttle. So we can be like, okay, cut it, we can do it. So now we have a problem is that our source, aka producers, no longer have control. They can no longer match to our demand, because sun is like, bro, I feel like it or I don't feel like it. Wind is like, I feel like it or I don't feel like it. Now so this creates a very serious issue where how the heck you match two intermittent thing, basically, where it's like, is it actually working or is it actually working? Like both of them have to be perfectly synced or grid will go down. So that creates the issue. Now, back in the days, the early era of wind turbine, we used to have inertia in wind turbine. So the idea was that you're going to have a wind turbine and that's going to have a blade that has a lot of angle control. So it will go through a gearbox and it will try its darn best to maintain the RPM, whatever the RPM may be, let's say 1500 RPM. And if the wind speed changes, it will change the blade angle, still trying to maintain that RPM to be at that point. Benefit was, it was adding inertia. So if you had anybody adding load, this will slow down and it will stabilize the system. So frequency will never go down. But with that system, the issue was that gearbox was expensive AF, maintenance was high AF, and it used to break, catch on fire, things of that nature used to happen. Because again, you are fighting two intermittent forces. Wind could be like, oh, you really want to slow me down? Or sometimes your power plant will be like, yeah, I don't feel like it, there is no load. So then it's like free spinning, very high speed. So we reached a point where it's like, what the hell we to do? In between, basically from 2005 to 2015, I would say, people tried doubly fed induction generator. The idea was, you have a generator and you have a rotating turbine, basically rotor, that's rotating at whatever RPM the blade is. So you let it free. Basically, you still has a step down, but you do not control it. It's like, okay, if it's rotating faster than it should do, it will have a counter rotating signature. Basically, there will be a small inverter that's going to figure out what's supposed to be the frequency, 50 hertz. Generator is trying to make 60 hertz. Okay, feed 10 hertz in counter rotation. So it will slow down. Yeah, like it's convoluted. Yeah, we had to do that. Now we just gave up on it. It's like, okay, yeet all of that. Now have almost a BLDC kind of topology where it's just a freaking generator. It does not care about the frequency. And then you have an inverter that is a grid tie inverter. The grid is trying to maintain inertia. Now you're like, okay, doesn't that give the same problem as solar panels? Yes. That's the problem. We do not have inertia anymore in the grid. The more solar and more wind we add, the more floating things become. One glitch can trigger a cascade failure, because these things are not primary source. So without the primary source, as in like big, giant, honking, big ass turbine spinning their ass off, these things are vulnerable. They are basically, hey, are you sure you are 50 hertz? Hey, are you sure you are 50 hertz? So it dips. Again, load happens. It starts to dip. It could cut out. It's designed to cut out. It's supposed to cut out. But problem is, now if you have a lot of solar farm, one cutout can literally trigger a cascade failure where almost all solar can go out. That will trigger such a backlash that all the remaining power plant could run, and you can have a, what we call cascade failure. And has happened. In small scale, it has already happened, where one glitch in some small farm is like triggered a cascade where hundreds of megawatt went offline, because it's designed to do that. Because these things are not primary producers. We still rely on coal as primary producer, or hydro dam as primary. Basically, big as spinning mass to actually be the primary signal that gives signal to all of these to provide power. So, and you're like, wait a minute, that makes our world very vulnerable. Yes, it is. Yes, it is. Without grid inertia, we are playing dice. And yes, people are already reaching that point where it's like, oh, because early days, everybody's like, oh, we have hundreds of gigawatt of coal. Now we are adding 1 gigawatt of solar. Who will care? Now we have like, oh, hundreds of gigawatts of solar per year. And now we are removing coal. Now the grid is like, bro, the few we have, it can be overwhelmed. Inertia has a limit. And again, if you too much oomph is drained, it will trip. Generator circuit breaker would be like, yeah, yo, tick, and boom, cascade failure. So if we do not fix this, our grid will become very fragile, and minor faults that used to happen 24/7 into 365, or somewhere here, somewhere there, which nobody gave a damn about, computer automatically fixed it to like cascade failure, where you can have whole sector going down. So we have to do that. And another aspect is these puppies, the coal power plant or thermal power plants. We poured a lot of money into these, and till very recently, and I mean recently as in 2010, or heck, maybe some power plant was just got completed in 2020. So if we're gonna just like yeet them, or like, okay, abandon ship, problem is the amount of money these things consume is bonkersly high, and ROI is not as quick as solar farm or even wind farm. These take a very long time to do ROI, because they have like, what we call round the clock power. They have very high value. So they can be expensive, and they do run for a very long time, let's say 50 years minimum. They have ROI of like, let's say 10 to 15 years, or sometimes not have ROI if you are running in South Africa. So lot of money and lot of jobs. They're placed in remote location. So you literally have a scenario where hundreds of people go into working into this. Those to facilitate those 100 people, now you have a small colony. To facilitate that colony, now you have a small village. Things grow. And again, these are backbones of many small villages. Now again, not one, many, and in everywhere, be it China, be it India, be it America. So it's almost like mining equivalent. Back in the days, mining used to be like, whoa, mining town and all that. Now power plant towns, we have that, literally have it. So if you poof them, you are giving your country a very serious amount of debt, and you are also removing way too many jobs, which could create resentment, which could spiral out of hand. So there is a problem. Another aspect is we need 24/7 power. Wind has its own mind, sun has its own mind. So what do we have to do? And again, demand also has its own mind. So supply, YOLO. Demand, YOLO. So how do you stabilize it? You have to use a big ass energy storage. Without a big ass energy storage, we are stuck. So this is a problem, and it's a genuine problem. If anybody is saying like, oh, if we just added solar without any consideration, we will collapse the grid, they are actually telling the truth. Same with wind. So we have to solve it. So we come to E2S Power. Now this company is like, hey, during that time when you have surplus production, which hilariously enough does happen every day now. Every day during daytime, like California in 2024, daytime 4 hours done. 100% of California was solar. 100%, not 24%, 100%. And again, they could still produce more, but because it's not connected to a national grid, they could not dump it effectively, apparently, for some reason. But again, they had to do curtailment. During curtailment, all the owners, solar farm owners, wind farm owners, they have to cut down first, because again, highest priority is on the coal. They do not want to shut down coal. Why? Coal is the inertia. If you're like, okay, let me turn off the coal, yeah, grid will collapse. So they have to make sure the inertia is always there. So inertia takes priority. Nuclear takes even higher priority. Nuclear will never be throttled down. So you have nuclear, you have coal, peaker power plants, and then you have solar and wind. So solar and wind have their own mind. So they could literally have a scenario where like GG amounts of sun, solar power is going bonkers, GG amounts of wind. At that same time, now you're like, yeah, dispatcher will pick up a phone and be like, hey, disconnect this solar farm. It has happened. It's what we call curtailment. It's like, it's automated process, but it does happen. At that point in time, if you're still sending electricity, you will get fined. And at that point, you can buy electricity for very cheap. They want to sell you at that point in time. Because if they're selling successfully, it's better than nothing. It's like, oh, instead of making $0, I will make few cents. I'll take that few cents. So, and again, you do not want a scenario where everybody has to shut down, because again, then will reduce the ROI, return on investment, which will trigger a cascade failure where in future, nobody will build farm. It's like, hey, it's no longer profitable. It will happen. So the idea is there is a point in every country that is growing with renewables, they are reaching what we call super cheap, abundant renewable energy. Meaning if you can buy energy at that point in time, peak energy, they will give you it for free. like let's say price is X, they can give you 10 by X. So you can get 1/10 of the price. So buy power at that point in time. Store it in thermal medium. What thermal medium? Originally they were trying with some weird medium where it's like, what if you have graphite which has aluminum which is doing phase change? Problem with that is aluminum does not melt at very high temperature. It melts at 800 degrees Celsius, not high enough temperature. So they abandoned that idea. That's why if you watch this company's old video, they are talking about this weird material. Now they are talking about normal graphite. So thermal medium will store the energy. And what is the duration? The duration is measured in hours. It can stretch up to a week. They're not planning this to like, okay, absorb all the energy during summer and dump it in winter. That's not the plan. It's not for that duration. The duration is ideally you should have enough a week of a kind of buffer, meaning you can have like a lot of solar someday and it's like, I got this, no curtailment, I got this. And then you have like, you know, some event happened, you have very serious power draw in the evening, it's like, I got you fam. It dumps all that energy. And again, if done correctly, if the size is right, it should be able to store enough energy to cycle through 1 or 2 bad days. Meaning, if you store an energy in it, it should be able to like, okay, no sun today, only let's say cloudy weather, no solar energy today. It's like, I got you. No wind today, I got you. For 1 or 2 days, it should be able to do that. Which is again, for many scenarios, that's more than good enough. That's all we need. And it's like, ironically, nuclear power created that solution, which we call pumped hydro in 1977. We just never used it. So this is something like that, although it does have lower what you call charge efficiencies, meaning you will lose a majority of your energy. You buy 100 megawatt hour, you cannot sell 100 megawatt hour, if lucky 30. So it does have what you call poor round trip efficiency. So how do you recover energy from it? You dump energy, electrical energy into it, it heats up. Okay, what do you do? After that, you turn that heat into high temperature, high pressure steam. Basically, this pressure steam is designed for steam power plant. It's not designed for anything else. It's like the whole targeting, the whole engineering is like you get a high, basically steam exactly as you get out of a coal furnace. So that's the idea behind it. Basically, you have coal thermal power plants, you heat the coal part, you put this puppy in. Nothing else changes. You have same feed water pump, you have same cooling tower, you have same generator, same turbine, same substation. Nothing changes. And yes, all substations are two-way by design. So do not worry, it's like how the heck substation will be, they're two-way by design. So it's like all you do, you heat the coal part, nothing else changes. Not the generator, not the turbine, not the plumbing system. Of course, you have to do new plumbing, but nothing inherently changes. So, and this adds one of the greatest thing, spin mass inertia, meaning you can keep this puppy running. Of course, you will, because of the slow startup and shutdown time, it's generally not advisable to turn it off. It's like you always want it to be spinning. And be mindful, having that just spinning, no load on it, just spinning, free spinning, that is still good. Why? Inertia. Now your solar inverters is like, is there anyone screaming in the grid that is like primary? This is like, I am the primary. It's like, I got this. Trust my inertia. Build on my inertia. This puppy is like, I got you fam. So during daytime or wind time or whatever have you, this is inertia. You can keep spinning it. And when you no longer have power, you drain the energy from that. It's like, got this. So spin mass inertia, that allows large scale, renewable deployment. Without that, we cannot do it. And how big these things can get? Well, they can start with basically the power output, meaning how much oomph it can dump is directly limited by the substation. So if the power plant was designed for, let's say, 1 gigawatt output, that's the maximum you can do. Again, sometimes you may have a high voltage transmission line that has spare capacity, so you can upgrade the transformer and get more oomph out of it. Generally, you won't. So assume whatever the coal power plant it is, whichever you are doing this change, that coal power plant's a rating. Let's say it was 50 megawatt, 100 megawatt, 12 megawatt, whatever have it, that becomes your power limit. That's how much oomph you can do. However, what about duration? So that gives you megawatt. What about megawatt hour? That can be free scale, meaning if you want to, you can just keep making it huge. Where it's like, okay, this puppy stores power for, let's say, a whole week. So if this whole sector, all the solar in this sector stops working, it's like, I got you. I can wait out the rain. I got this. That can be done. So your watt hour is completely independent of watt. So that is also really desirable. Meaning if some scenarios, all you need high frequency trading, whereas like watt hour is not that important, you focus on the transformers. You're like, hey, we need long storage. It's like, I got you fam. And it's cheap, long-lasting medium is just graphite. Not even fancy graphite. It's like graphite with aluminum into it. It's like, no, graphite. Take it and go. And it has no risk to environment, because what happens if graphite burns? Carbon dioxide, not toxic. It's not conflict mineral. It's not toxic. It's just stuff, carbon. You do not have to worry about it. Nor it's harmful to people. And it keeps the local jobs and economy stable. If you invested billions of dollars, and yes, coal power plants are that expensive. If you spend billions of dollars into it, you do not want to poof that, because that becomes inflation for your future children and they will hate you for it. So you should not poof the jobs. And you should not just poof, oh, we built this giant architecture, let's just poof it. No, you do that. And it's cheaper than battery alternatives, not only because again you can scale the megawatt hour to very large scale, but it also gives you inertia. You cannot get inertia with a battery system. You can program the inverter to be like, okay, do not take signal from the outside, have an atomic clock there to be like, okay, now you are the source, but it does not have that physical reliability to it. This has the physical reliability. It is exactly what we had, now cleaner. So this is the company's philosophy, where it's like, okay, you have coal power plants, eat the coal part of it, still have the power plant, which acts as a battery, grid stabilizer, inertia adding system. You no longer have to poof the job, you no longer have to cause pollution. Win, 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 win. And it's cheaper, long lasting, and it can go to very large scale. So how they are achieving this win, 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 win scenario? Well, the idea is core is conduction, meaning you must have seen Antora's Energy, and there is another fire brick company that is building this similar kind of test system. They are always using gas to conduct heat from one place to another. In Antora's case, they are using photons to conduct energy from one another to another. Yeah, that's the weak link. If you pay attention to the steam temperature and pressure, the temperature is not that high. Like if you pay into coal furnace, the furnace fire, the actual whoosh, that is very high temperature. That is upwards of 1500 degrees Celsius. So why the heck water is only at 600? Because conduction is not the primary mean. You have radiative heating, you have hot gases, but it's not touching it. Like the fire is not going through the water. So water is not very, it's not getting the full love. Basically, you have very serious temperature delta drop. But here, they are touching it. So temperature delta drop is negligible, meaning the graphite blocks heats up. There is no air, there is no photon, there is water going through it, meaning there is pipes literally in the graphite block. So water is touching it and it's at high pressure. So basically inefficiencies in conduction is removed. So temperature delta requirement, meaning in other systems you had to heat it up to 3000 degrees Celsius, then you get 1500 degrees Celsius as a furnace, then you had 600 degrees Celsius water. Here it's like, bro, I can give you 600 degrees Celsius water even though I am at only 700 degrees Celsius, because of the improved transfer efficiency. And if you know anything about graphite, it's already used as a heat exchanger because it's so goddamn efficient. So it reduces temperature delta, meaning you no longer need to heat to bonkers temperature of 3000 degrees Celsius. You can, and again, that will improve your density, but you no longer need it to. Just like, you could. It's basically, it reduces your spare capacity. Think of this way, 0 to 3000 degrees Celsius, and you cannot drop below 1500 degrees Celsius. That means you lost 50% of the energy. You cannot let it cool down too much, because again, the turbine will stop. You do not want it to stop. So here it's like, okay, now instead of 3000 to 1500, it's 3000 to 700 degrees Celsius. That's a lot of usable space. So that's a very big advantage. The heaters, they are physically touching it. Water, physically touching it. So this physical conduction is giving them efficiency. And graphite unit has embedded unit, and how they are making the temperature part, they are flowing through multiple stages, same as that fire brick company. So the idea is, you will get overheated steam if you directly send through the first one unit. So what do? You send it through one unit and you send it to another half depleted unit. So instead of getting 700 degrees Celsius out, you will get 550 degrees Celsius out. So as the primary source starts to cool down, the heat starts to flow backwards. That's why conduction is such a critical aspect. And then you still get 500, meaning this can cool down to very little and you still get 500 degree. Multiple stage allows you to control the output temperature very precisely. It's like an actual throttle valve. You no longer have like, okay, it's starting to cool down. No, it's like either it has power or it has no power. It's almost binary as you want it. The output temperature, see, you can see the main temperature is going down, but the output is always staying the same. Now, again, I do not think it's exactly 550 degrees Celsius, but reasonable enough. So multi-stage allows you to have temperature control, and they are only going to replace the boiler with power plant. Nothing else will change. So that's the tech. Surprisingly simple, non-convoluted, and simple. So what about India? Now, India Power Corporation Limited, a 105 years old company, they got in bed together with this, and E2S started a joint venture in West Bengal. It's in Asansol. You can find it in Google Map. So the unit is, this puppy is 250 kilowatt hour, and they're supposed to hold energy for 4 hours. Now you may be like, okay, I'm talking about megawatts, this is freaking kilowatt and only 4 hour, what's the point? Well, this is not a running unit, so to say. This is a proof of concept on commercial scale, meaning can it maintain the temperature it's supposed to maintain, can it absorb? Because again, in principle, this can also work in reverse, meaning if let's say demand goes down too much and you still had like boiler firing, because there will be a lag. Your demand went down, but a boiler will take time to cool down to a lower coal flow. So at that point, what do you do with wasted energy? You waste it. Or here, you're like, okay, what if I heat the block? So that becomes a smaller buffer. So that's what they are testing. Can we do it with electricity? Can we do it with spare heat? That's why the people talking about it. I have linked an amazing video down below of this individual, this exact team. And they're like, it can take thermal energy or it can take electrical energy. Idea is electrical in future. Right now they have spare thermal, so dump spare thermal into it. So, and this is only supposed to showcase two things: plug and play, and does it actually work? The target is 540 degrees Celsius and around 150 bars. Now be mindful, the bars is controlled by the feed water pump. So, and you were like, okay, it's not that high. It's not need to be. The power plant is a small power plant. It's if I'm not mistaken, 12 megawatt power plant. It's not a huge power plant, high pressure power plant. And the idea is bring down the cost of RTC power. What does RTC mean? Round the clock, meaning we have enough solar in India, and if solar is reaching curtailment, that's why we are slowing down. It's not that, oh, India no longer have money. We got money. It's just that nobody wants to build solar farm anymore. It's like, hey, ROI is now longer because again, at the afternoon, everybody has shut down. If this becomes a success, all the coal power plants that we are deprecating, we're like, okay, convert it into battery. So during daytime, it's like, oh, we have so much surplus power. It's like, buy it. Keep buying it, bro. Keep buying it. It's like, what do we do in nighttime? It's like, bro, I got this. Dump energy back in. And you have grid inertia. With energy storage, shut up, take money. So that's what we are doing. So, and it's surprisingly quickly. 2 years ago, the memorandum of understanding was signed. Now it's deployed in testing. It's fast. So what can we expect in the future? Well, reality is this technology crossed what we classify as TRL7 or technology readiness level, meaning all technology readiness level has generally 9. 9 simply means you pick up a phone, bro, I want it. They're like Amazon 24-hour delivery. That's readiness level 9. And TLR1, it works on a principle on a lab. So they have crossed a lot of things, and this is a point where they are touching real world, and specifically, does it work in commercial setting? It's one thing to say that our wave flow technology, they have weird name with this. Wave flow technology is rather than just multi-stage heat exchanger. It's like we can control the temperature output. Okay, you did it in lab, but here's the, does it work in commercial random scenarios? If it works, awesome, GG. And I'm reasonably sure they will find certain flaws where it's like, okay, temperature is dipping or it's overheating, and they have to fine tune it. That's supposed to happen. That's why we are at TRS7. But if you are at TRS7, the likelihood of you're not working out, it's almost zero. And be mindful. One thing everybody will say, oh, it has poor round trip efficiency, which is factually true. Would I prefer this compared to pumped hydro? Hell no. Pumped hydro is 10 times better. But again, it has so much bureaucracy, nobody even talks about it. It's like the bureaucracy will take 15 years just to start the paperwork. So it's like, bro, don't waste time on that. I get it. It's undesirable, but it is what it is. So what is the next best tool? This. So low round trip efficiency does not matter when you are dealing with decommissioned power plant, meaning these power plants, many of the power plants are still new, meaning they were only completed in 2010 or some in 2015. You are just going to yeet them because of environmental factor. The money that was spent, they're still spent. It's not going to come back magically. You cannot sell these things. So that creates a very serious issue. You like a very serious inflation issue. You do not want to just like, oh, now we have 3,000 crore of debt. That's not acceptable. I mean, like, you can force it on people, but people will hate you. So that's there. Another aspect is power curtailment. So you have these two bad options: power curtailment and power plant deprecation. What if you do not have this? What if you're like, hey, you have this, add money to it. Of course, you have to spend money into it to add this unit, and this works. This just works. It does not pollute the environment. It just works. It does not give you, basically, it also solves one of your weak links, where it's like, how do we have grid inertia? It's like, bro, I got this. I was the one who had it. I am the one who is still providing you. Do not worry about it. I got this. That's like, shut up, take money. So in those sort of scenarios, like, we cannot add more solar because we no longer have grid inertia, solved. We no longer can add solar because we have to do power curtailment, solved. We have coal power plants that we have to solve. So that's why that round trip inefficiency that you have, it's no longer a big issue. In contrast, you have to think thoroughly. It's not for public use, it's for power distribution grid. At that point in time, it makes sense, economic sense. Physics, engineering, economics, it makes economic sense. Another aspect is how many plants we are talking about. India has 180 active units last I checked. Again, plus and minus few will always happen. Globally, we have 2,435 active. So that's a lot. And there are generally three reasons why coal power plants are shut down. One, environmental, meaning if you have like ugly coal, sometimes people do unluck out and you have sulfur, mercury, and these things start to emit so much that people start to actually going poof. Then we have to shut it down. Rarely happens, but does happen once in a while. That's pollution. Second, you run out of water, very likely to happen. Third, the coal became too expensive, which again, believe it or not, does happen. So in this three scenario, what about the water part? You solve the coal problem, you solve the pollution problem. What about the water? Thankfully, we have the technology. Technology is called air condenser. If you add air condenser, yes, again, another expenditure, but again, fresh water is priceless. So whatever cost you are paying right now, it will do ROI. And this is India's first. Again, India is a bit behind in this. We were always water rich, but we no longer are water rich. So we have to be like, okay, now we also have to invest into these. This is huge. Let the photo fool you to thinking this is small, but if you Google it, it's in North Karanpur. It's in Jharkhand. This is huge. This building is huge. It's almost like a jumbo jet on pillars. It's huge, bonkersly huge. Like, let me be very clear that it has multiple fans. Each of the fans is the size of a helicopter. So these are huge. Like, we generally do not expect the size of this radiator, but it is like, I got this. Again, it's designed to dump megawatts of heat. So it's a very big benefit. No longer you have cooling tower waters. It's like done. Now, does it eliminate water consumption? Not really, but it goes from consuming hundreds of liters per hour to maybe few liters per day. Okay, system becomes fully sealed. So at this point in time, now you can sustain it forever. So future is very optimistic here. We invested bonkers amount of money into this. Use it. We invested bonkers amount of money into this. Keep using it. We have a technology that is almost ready, almost to a point where we are fine-tuning it. It's no longer like, oh, it does not work. We crossed that threshold. At this point in time, oh, what is the issues here? Like, we are fine-tuning it. It's like, how do we control the algorithm? How do we control the SCADA system where it has input and output completely balanced? How do we make sure we shut down if something bad happens? All those things. We are fine-tuning it. Of course, I do expect it to take time, and be mindful. Efficiency grows up the higher the capacity you make it. Why? Because you're going to have liters, as in volume, bigger. So you're going to have let's say 100 gallon, or gallon would not be right term. Okay, let's say 100 gigaliters of capacity. You have insulation. Now you made it 10,000. Benefit is your surface area goes down. So if you remember the old school mathematics, if you increase this diameter or increase the size of a cube, the surface area goes by square, but the volume goes by cube. So your inefficiency of thermal losses goes down, meaning now how long you can hold the energy also goes up, meaning you can go from, hey, I can only hold energy for a few days to like almost a month. You will be able to jump through a month. So there is a lot of potential here. Technology is almost ready. We have half of the infrastructure already built. So it's a very good innovation where we're like, rather than recreating random BS, it's like, hey, we knew how to give grid stability. Let's just keep it. It's like, we need energy storage. What if we just use the same thing? So this is really optimistic scenario. It's like, okay, we have a problem. We solved it. I'm very happy with this. So this was my presentation on basically the current partnership between India and thermal energy storage systems. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me a disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.